that he arrived at the Schrodinger equation, the wave equation, from intuition. He then obtained an equation where he found that the only energy levels that are stable are the energy levels that Niels Bohr has predicted with his theory. And Niels Bohr theory was trying to give a physical interpretation to the emission of different frequencies of light from electrons changing orbits in the proton, around the proton. So as electron would go from one orbit to another, they would release quanta of energy, and they measured those frequencies, and they found that they followed a series that Niels Bohr have mapped by an equation that says these are the energy levels because those energy levels correspond to stationary electron waves that are circular around the proton. What Schrodinger did with his equation is he found that not only there are circular wave, stable wave configurations, but he found all sorts of configurations for same energy. You could have an electron wave configuration that had different angular momentum, but still the same level of energy. And so there was different ways that the wave function would show itself through space for the same energy. So Einstein said that his paper, the paper that Schrodinger wrote in 1926, it was an idea of genius. And Schrodinger arrived at the equation while he was on vacation, actually. During that time, he was hopping from university to university to try to find a job as a teacher. It was hard to find jobs that paid enough. So I think he was either an assistant or a teacher at that time, but he eventually went on vacation in the mountains, and he had like some mysterious girl who came to his to where he lived, but he never said it was who. And he came up with those orbitals, those electron orbitals, and his equation. And he also came up with the Klein-Gordon equation for relativistic wave functions, but he found that the energy levels, or he found that, so he found that the stable energies of the Klein-Gordon equation didn't match the energy levels found by the Bohr theory. But what would happen maybe in 1935 or something is that Dirac, a young engineer who transitioned to physics, he generalized the relativistic equation by treating the electron as a 4-component wave function. So instead of having one value at each point in space, it had 4 values. And in doing that, he was able to find an even more precise spectrum of energy. So the stable energies of Dirac's equation were even closer to what was predicted. The energy levels given by electrons changing orbits, changing energy levels, emitting specific frequencies of light. So Dirac's theory had a more precise saying on those levels of energy, those finite levels of energy. And after, well, let's return to 1926 when he wrote his paper. He then was probably eligible to win a Nobel Prize, but he needed to prove that his Schrodinger equation can actually have an impact. Because before Schrodinger, Heisenberg has already formulated an equivalent quantum descriptions of particles using matrices treating position, and that was the matrix mechanics formulation of quantum mechanics. And it was written in the book that Heisenberg had that idea while he didn't sleep at night and went for a hike in the mountains. And he was like, as he finished the hiking, the idea came to him and he was really elated. He came up with his matrix mechanics, and then when Schrodinger arrived at his equation, Heisenberg was put off by it. Heisenberg didn't agree to it, but later Schrodinger proved that matrix mechanics of Heisenberg was equivalent to his differential equation. So the operators would actually be differential operators on wave functions. I actually looked on AI and asked, like, is there an advantage to working with the Heisenberg matrix mechanics? And it said that in systems where there's a discrete number of particles and where the particles are in a lattice, where space is just described by discrete steps, you cannot go in between steps. Matrix mechanics shows more utility there. But yeah, so Schrodinger proved that his differential equation was equivalent to Heisenberg.